Today we will be continuing with the Galerkin's method, and after that we will go on to one dimensional finite element problems. We will see how the one dimensional finite element problems are solved using both the Rayleigh-Ritz method and the Galerkin's approach. If you remember, yesterday I had introduced this expression, and I said that when we are talking of this weighted integral, the integral of the weighted integral of the error term, this in the case of elastic three dimensional problem will come to this equation. That is, this first part of this part is the equilibrium equation in the x direction, this is the equilibrium equation in the y direction, and this is the equation in the z direction. Okay, and each of these terms multiplied by the corresponding weights in the x, y and z direction, and then integrated over the volume. Okay, so this is the volume integral, and this we said it should be equal to 0. Now, in order to simplify this integral, we will be using what is called the divergence theorem, and I mentioned the divergence theorem is this theorem. That means, if we have a term alpha and a term theta, and we want to evaluate the volume integral of del alpha by del x times theta dv, that will be equal to minus of the volume integral of alpha times del theta by del x, that is this term, derivative of that with respect to x, into dv, that is volume integral of this term plus the normal in the direction of alpha or n alpha multiplied by alpha, that is this term, into theta into ds, that is the surface integral of this. Okay. So, this is what we call as the divergence theorem. Now, if we apply this divergence theorem to the terms coming in this equation, this first term, this one, del sigma x by del x multiplied by phi x multiplied by dv. Okay, that is, this term is, I will just repeat it here, del sigma x by del x multiplied by phi x multiplied by dv. If you compare this with the term that you have here, your alpha is the same as sigma x, the theta is the same as phi x. Okay, and if I put these two over here, this first term would become something like this. In this expression, instead of alpha, I have put sigma x. Okay, so I get integral of sigma x, instead of theta I am putting phi x. So, del phi x by del x times dv, the volume integral of that with the minus sign, okay, plus the surface integral of n alpha alpha theta ds. Now, n alpha in this case will become nx, alpha is the same as sigma x, theta is the same as phi x. So, nx sigma x phi x multiplied by the surface term ds and the surface integral of that. Okay, so, the first term in the expression, that is this term or this term, can be simplified to this term, this expression. Okay. Similarly, the next term that is there, that is this, del tau xy by del y multiplied by phi x multiplied by dy. Please, sir, later. The second term, del tau xy by del y, that term will simplify to an expression of this type. Okay, tau xy will come here, tau xy into del phi x by del y, because here we have got the derivative with respect to y. So, tau xy into del phi x by del y multiplied by dv and the volume integral of that, and the second term that we will get will be ny tau xy phi x ds, again the surface integral of that. This way, for all these terms, for 3 into 3, for these 9 terms, we will be able to get 9 expressions of this type. Okay, and plus we have got this term fx phi x, so this I will write here separately, plus integral of fx phi x dv volume integral plus volume integral of fy phi y dv, and the third term is this, that is plus the volume integral of fz phi z dv. Okay, so I will have a set of terms like this, plus I will have 3 terms like this. Okay. Now, if you look at if you look at these terms, these 3 terms I can just write them as integral of f transpose into phi dv. Okay, your phi, or just I'll write it as integral of phi transpose times f dv. Okay, where phi is nothing but phi x, phi y, phi z column vector, and f is nothing but fx, fy, fz transpose. Okay, so these 3 terms can be written like this. Okay, now if I look at these terms, if you remember the definition of epsilon, okay, if you have any deformation u, the corresponding epsilon is u, the vector u v w. The corresponding epsilon or the strain vector, this we said would be epsilon x, epsilon y, epsilon z, lambda yz, and so on transpose. Okay, again epsilon x we said is del u by del x, epsilon y is del v by del y, epsilon z is del w by del z. Okay, similarly we have terms for lambda yz and so on. Okay, now here we have got a term on phi x, that is del phi x by del x. Okay, and we also said that the phi, that is the weights that we are giving, are consistent with the boundary conditions. Okay, that is one of the constraints that we had in the Galerkin's approach. So we can effectively say that we can take this phi to be equivalent to a displacement, and del phi x by del x is the strain in the x direction that will be there in the object if this phi was given as a displacement. Okay, so if I write an expression for epsilon of phi, this would be equal to del phi x by del x, epsilon y term that will become del phi y by del y, epsilon z term will be del phi z by del z. The lambda yz term, here what we would have got would have been del v by del z plus del w by del y. Okay, this term would have been lambda yz. Corresponding to that we will get here del phi y by del z plus del phi z by del y, and another 2 terms like this. Okay, so this vector is a strain that would be there in the object if phi was the displacement that was given, or the phi was the displacement field that was there in the object. Okay, so epsilon of phi, that is not the actual strain in the object, but the strain that would be there if this displacement phi was given. Okay, and if you look at these terms, first, second, this term is nothing but the component of epsilon phi. Epsilon phi is the vector, so the first component of that is the component in the x direction. Okay, this is nothing but a part of the term that we will have in the end, that is corresponding to the last term is lambda xy. Okay, a term that we will have in the end, that will have this term of del phi x by del y. Okay, so if you look at all these terms that we will have, we can collect all these terms together and we can say that this would be equal to minus of the integral of sigma transpose multiplied by epsilon of phi multiplied by dv. Okay. Now this epsilon of phi, as I said, is a strain that would be there if phi was the displacement that was given to the object, and we have already said that this displacement has to be consistent with the boundary conditions, and this sigma transpose is the actual stress in the object, the actual stress distribution in the body. Okay. Now from this again, the first term of sigma transpose is sigma x. The first term of epsilon phi is del phi x by del x. If I multiply these two, I get the first term here. Okay, the second term of sigma transpose will be sigma y. In the second term of epsilon phi will be del phi y by del y, and that will be the next term that we will have over here, minus integral of the volume and so on. Okay, so all the term that one gets from this will be a term that we will be getting from this column. Okay, so this, all these terms can be compiled into one single term, and that is this term. Okay, and as I said, this phi, this is possibly a displacement field that we are giving to the object, and if you are familiar with the principle of virtual work, this phi is actually the virtual displacement that we are giving to the body. What we are calling as weights earlier, that is actually a virtual displacement that we are giving to the body. If you give it a virtual displacement, then the strain due to that virtual displacement is the strain epsilon phi. Okay, and this sigma transpose is the, or this sigma is the actual stress in the body because of the existing loads. Okay, this sigma and epsilon are because of two different factors. Epsilon of phi is because of the virtual displacement, sigma is because of the actual loads. Okay, this is how we get this one term, and then we will collect all these terms together, and what we will finally get will be an expression of this type, minus integral of sigma transpose epsilon of phi dv, the volume integral, plus volume integral of phi transpose f dv. This is the term that I just mentioned. This is this term. Okay, this has been collected by taking these three terms together. Okay, if I take these three terms together, I will get this term, and if I collect all these columns, the terms in all this, the term in this column together, I will get this term. Okay, the remaining terms I will just write them down as they were, and what I will get will be plus the surface integral of nx sigma x plus ny tau xy plus nz tau xz multiplied by phi x plus nx tau xy plus ny sigma y plus nz tau yz multiplied by phi y plus nx tau xz plus ny tau yz plus nz sigma z multiplied by phi z, this whole thing multiplied by ds. Okay, these are the terms I will get by collecting these terms. Okay, these terms are nx sigma x phi x that is term I nx sigma x phi x. This term is ny tau xy phi x, this is ny tau xy phi x. Okay, this I have collected all these terms together to give me this surface integral. Okay, and then we are saying that all this will be equal to 0. Okay. Now let us again look at the equation that I had given in the beginning of the first lecture on finite elements. That is, we had given a set of equations like this: nx sigma x plus ny tau xy plus nz tau xz is equal to Tx. Okay, this is for any element on the surface. We had said that if we have an element like this, and if we write down the equilibrium equation for this element, we will get this equation in the x direction. We will get a similar equation nx tau xy plus ny sigma x plus nz tau yz is equal to Ty. Okay, so ny sigma y plus nz tau yz will be equal to Ty, and a similar equation for the third direction. Okay, this is for the traction or the tractive loads acting on the surface, that is forces per unit area. Okay, these are the tractive forces acting on the surface. But if there are any point loads on the surface, then our equations will be different. Okay, if in addition to the attractive force we have a point load acting like this, in addition to these equations we will have to write nx sigma x plus ny tau xy plus nz tau xz, all this multiplied with ds will be equal to a point load in the x direction. Okay, if you do not give any point load, okay, then if I integrate over the complete surface, over this surface, I will be getting a term like this. It will be equal to the total tractive force in the x direction. Okay, but if I have a point load, then effectively I will have to multiply this by the surface area, and that will be equal to the point load in the x direction. Okay, similarly I will get another two equations like this. Okay, so now if I look at these terms, okay, if I look at these terms, for all the tractive forces, I can say that this term is nothing, this term, and that will be equal to Tx. Okay, this term is nothing but this term, and that is equal to Ty, and similarly this term is not equal to Tz. Okay, but in addition to that, for the point loads, since I am calculating a complete surface integral over the surface, the point loads will give me additional terms of Px multiplied by phi x and so on. Okay, so this surface integral will be equal to, I get surface integral of Tx phi x plus Ty phi y plus Tz phi z multiplied by ds, plus for the point loads I will get Px multiplied by phi x plus Py multiplied by phi y plus Pz multiplied by phi z, and since the point loads are discrete, I will have to carry out a summation over all the point loads. Okay, if I have a number of point loads over the complete surface, if I have a surface like this, a body like this, I have a number of point loads. For each of these point loads, I will get a term like this. So I will carry out a summation over all the point loads. Okay, and these phi i's will be the phi at each point. Okay, so if I make these two substitutions, my integral, this integral term these two terms will become, now this is nothing but integral of, I can write this as phi transpose T ds, okay, because I am using the T will be nothing but Tx, Ty, Tz transpose, okay, and this would be this plus sigma Ti phi I going from 1 to n if I have n point loads, okay. So this expression will give us these two terms, and this complete expression, okay, that will become minus of volume integral of sigma transpose epsilon of phi times dV plus volume integral of phi transpose f dV plus surface integral of phi transpose T ds plus sigma I going from 1 to n Pi phi I, and this term should be equal to 0. Okay. So this would be the expression that we will get by evaluating the integral that we had in the beginning, that is integral of W e dV should be equal to 0. Okay. Any questions up to this point, this derivation? Okay. Now if we look at this, I said that if we give this object a virtual displacement as phi, okay, if I have an object like this and this has some boundary condition that, let us say, this part is fixed, maybe this part is fixed or some such thing, and we give it a virtual displacement consistent with these boundary conditions, and that virtual displacement is phi. This strain is the strain caused by this virtual displacement, okay. Again this is also the virtual displacement, this is also the virtual displacement, and this is also the virtual displacement, okay. So if I look at this term, the first term, that is okay, this first term, this is nothing but the internal work done by the virtual displacement. When you give the object some virtual displacement, then this is the internal work done, that is the work done against the internal stresses, and these three terms give us the work done against the external forces. Okay, let us say if I have some point load over here, or if I have some body forces acting like this, and I try to give this object a virtual displacement, okay, then the work done against these forces, against these body forces, will be given by this force multiplied by the distance. Okay, they are the body forces multiplied by the virtual displacement we are giving, and we will integrate that over the volume. So this is the work done against the body forces. If you look at this, there is a question there? Yeah.
Can we really separate the external work and the internal work? Because as soon as there is an external body force acting,
yeah,
it straight away gives rise to internal stresses in the body.
Yeah.
So how can we really?
Okay, I'll just come back to your point in a minute. Okay. Now if you look at this term, this is the work done by the virtual displacement against the tractive forces. That means there are any forces acting on the surface, that is a pressure or force acting on a per unit area basis, then this term will give us a work done against that, and this will be a work done against the point loads. Okay. So this complete these three terms will give us the external work done.
What's the first term for these three terms?
This one?
Yeah.
This is for the body forces. That means, let us say gravity, work done against gravity, okay, or there might be some magnetic forces acting on the body, which will again be on a per unit volume basis. Okay, so all those forces are the forces coming under this F, that is the body forces. This P are the tractive forces, that is forces acting on the surface, and these P's are the point loads acting on the body. Okay. So these three terms will give us the external work done. Okay, so if I look at this, I get the internal work done or minus internal work done plus external work done is equal to 0, or the internal work done will be equal to the external work done. Okay, and in fact this is basically a principle of virtual work. A principle of virtual work, whenever we give any virtual displacement, the total work done will be equal to 0. Okay, so what we are saying, the total work done, that is basically equal to 0. Okay, a part of that is what we are calling as internal, done against internal forces, and a part of that is what we are the work done against the external forces. Okay, and that will give the answer to your question. Okay, the total work done by the virtual displacement will be equal to 0. Okay, so essentially this Galerkin's approach for elastic bodies boils down to the principle of virtual work for the elastic bodies. Okay, any question on this Galerkin's approach? Okay, so now we have seen two methods. One is the Rayleigh-Ritz method and the second is the Galerkin's approach. Just to recapitulate, in the Rayleigh-Ritz method, the final equation that we got, that was the equation for the potential energy term, and we said that the potential energy of the object the potential energy of the object Pe or pi, that is equal to u plus the work potential. Okay, and the term u is half of integral of sigma transpose epsilon dV, volume integral of that, minus the work potential is given by the volume integral of u transpose f dV minus the surface integral of u transpose t ds minus sigma ui transpose pi. Okay, this is the expression for pi for potential energy, and this we are using in the Rayleigh-Ritz method. And in the Galerkin's approach, we just got that minus of the volume integral of sigma transpose epsilon of phi dV plus the volume integral of phi transpose f dV plus the surface integral of phi transpose t ds plus sigma I going from 1 to n pi phi I is equal to 0. Okay, this is the internal work done, and this is the external work done. Okay, and the two should be equal, and the total work done should be equal to 0. Okay, this equation we will be using when we use the Rayleigh-Ritz method. This will be using when we use the Galerkin's approach, and we will see that using both these approaches we will be able to get the solution to the finite element formulation for different kinds of problems, whether they be one dimensional, two dimensional or three dimensional. Okay. Now what we will see is how these methods can be used for simple one dimensional problems. Okay. So for a simple one dimensional problem, okay, when we are talking of one dimensional problems, what we do is that if we take any object, we are talking of one dimensional bodies, we will basically be talking of rods. Okay. So let us say if we take a rod like this, we want to divide this body into a set of small one dimensional elements. So for dividing into a set of small one dimensional elements, we will approximate this by elements of this type. Okay, each of these will be treated as one single element. Okay, and we will assume that within this element the area of cross section of the element remains the same. Okay, that means let us say if I consider this element, this will be an element which will look like this. Okay, that means there is no variation in the area of cross section. Okay, so along the length of this element, its thickness and height would remain unchanged. That way, it will vary only in one dimension. Okay, that is why we call them as one dimensional element. If you want to formulate the same thing as a two dimensional problem, okay, then we can approximate it by triangles or quadrilaterals or something like that. Okay, those could look maybe something like this. Okay, but right now we are just talking a simple one dimensional formulation of this problem. Okay, so we will assume that there is no variation in the other two dimensions and all loads are also only acting in one direction. Okay, so all the loads will also be acting in the x direction only. Okay, so if I take any element, that element essentially looks like this. Okay, it is just a rod like element, uniform cross section. Okay, on this element, let us say this is my point 1 and this is my point 2. Okay, at this point, let us say the x coordinate, if my element is here, the x coordinate here is let us say x1, and at this point, that is let us say the x coordinate here is x2. Okay, what we will do is we will define a local coordinate system for the body. Okay, the local coordinate system would be that instead of talking of the x coordinate for this, we will talk of let us say the zeta coordinates. Okay, that means let us say in the center we will say we will have zeta equal to 0, sorry, in the center let us say here. At this extreme we will get zeta equal to 1 and at this extreme we will get zeta equal to minus 1. Okay, and zeta will vary linearly from one point to the second point. Okay, so a zeta will be equal to, you will find 2 times x minus x1 divided by x2 minus x1 minus 1. Okay, so at this point x is equal to x1, so I put x equal to x1 here, this term will be 0 and zeta will be equal to minus 1. At this point x is equal to x2, so x2 minus x1, this will cancel out, 2 minus 1 will get plus 1 over here. Okay, similarly at the center, that is x1 plus x2 by 2, we will get zeta to be equal to 0. Okay, so essentially zeta will be changing from minus 1 to plus 1 in a linear manner. Okay, here we have zeta equal to minus 1, here we have zeta equal to plus 1. Okay. If we look at this element, the x value here is x1, here it is x2. Okay. Now let us say in the final displacement that is given to this body, okay, because of the loading that is acting, there is some displacement throughout this body, some deformation throughout this body. Okay. Let us say the deformation at this point is q1 and the deformation at this point is q2. Okay. So the deformation here is q1, the deformation here is q2. Okay. Now if you know the deformation here and the deformation here, we are interested in finding a deformation at any point inside this element. Okay, the deformation at any point inside this, let us say, is given by u, and we will assume that this deformation is a combination of q1 and q2, depends only on q1 and on q2. Okay, so let us say we say it is a linear combination n1 q1 plus n2 q2. Okay, so deformation at any point inside this element is given by this linear combination where n1 is a function of zeta, that is equal to 1 minus zeta by 2, and n2, which is also a function of zeta, is equal to 1 plus zeta by 2. Okay. So, u, which is the deformation at any point inside this element, is given by n1 q1 plus n2 q2, where n1 and n2 are functions of zeta. Okay, what we are basically saying is that if I take any point inside this element, let us say I take a point here where zeta is equal to minus 0.5. If I put zeta equal to minus 0.5, I will get some value of n1. Okay, similarly, if I put zeta equal to minus 0.5 here, I will get some value of n2. Okay, for both these, for these values of n1 n2, I can put those values here and I will get some value for u, that will be the u at this point. And since n1 and n2 are varying linearly, this relationship gives me a linear variation of u along the length of the element. Okay, let us say if I plot u along the length of the element, let us say here it is q1 and at this point it is q2, along the length it will vary in a linear manner like this. That is what I am assuming right now. Okay, and similarly if I plot n1 and n2, at this extreme I will find n1 is equal to 1. Okay, but if I put zeta equal to minus 1, this will become 2 by 2, which will be 1, and at the other extreme n1 will be 0, because if I put zeta equal to 1, I will get 0. So, this is the variation of n1, and if I try to plot n2, I will find n2 will vary like this. Okay, n2 will be 1 at this extreme and will be 0 at this extreme, and n1 is the other way around, it is 1 at this extreme and is 0 at this extreme. At this point we have zeta equal to minus 1, here we have zeta equal to plus 1. Okay, and u is varying linearly from q1 to q2 along the length of the element. Okay, for one dimensional problem at the moment it is very straightforward, but the same principle will also be using for more complicated 2 dimensional and 3 dimensional problems. Okay, so we will be extending the same principle later on. Okay, these expressions n1 and n2, these are referred to as shape functions. Basically these shape functions are defining what is the variation of u, that is deformation along the element. I said it is a combination of the deformation at point 1 and the deformation at point 2, and I am assuming it to be a linear combination, that is I am using linear shape functions. Okay, let us say if in my element instead of 2 points I consider a number of points, let us say I consider 3 points, then I can give my deformation to be a function of 3 points. We will see that later. Okay, but right now we are taking linear shape functions and we are defining only 2 points on my element. That is why this element is also referred to as a 2-noded 1-dimensional element. Okay. So now I have u equal to n1 q1 plus n2 q2. If I know the expression for u, then I can find out epsilon, which is equal to du by dx. Okay. So let us find out the expression for epsilon. The equation that we have so far are u is equal to n1 q1 plus n2 q2, or we will use a vector notation and write it as n times q, okay, where n is a vector and q is also a vector, where n is the vector n1 n2 and q is the vector q1 q2 transpose. Okay. I have also mentioned n1 is equal to 1 minus zeta by 2, n2 is equal to 1 plus zeta by 2, and I have also mentioned that zeta is equal to 2 times x minus x1 divided by x2 minus x1 minus 1. Okay. From this, if I try to write down d zeta by dx, this is equal to 2 divided by x2 minus x1. Okay. From this, if I try to get dn1 by d zeta, it is equal to minus half, and dn2 by d zeta, it is equal to plus half. Okay, and epsilon, which is equal to du by dx, this will be equal to du by d zeta multiplied by d zeta by dx, which will be equal to, I have to differentiate this with respect to zeta. q1 and q2 are constants along the length of the element. Okay, but if I have an element like this, q1 is a deformation here and q2 is a deformation here. Along the length of the element, q1 and q2 are constant. Okay, so du by d zeta is going to give me q1 multiplied by dn1 by d zeta, which is minus half, so minus q1 by 2 plus q2 into q2 by 2, this whole thing multiplied by d zeta by dx. D zeta by dx is this, which is 2 divided by x2 minus x1. Okay, and this is 2's, the 2's will cancel and we will get q2 minus q1 divided by x2 minus x1. Again?
du by d zeta.
Du by d zeta.
Yeah. How do we get this?
How do we get du by d zeta?
So how do we get this minus q1 by 2 and
Minus q1 by 2.
Yeah.
Okay. I am differentiating this term. q1 is a constant, so I will write it here. Du by d zeta will be equal to q1 multiplied by dn1 by d zeta. dn1 by d zeta is minus half plus q2 multiplied by dn2 by d zeta. Okay. Any other questions? Okay. So now this is my expression that that is there for the epsilon. Okay. I will rewrite this expression. Epsilon is equal to 1 over x2 minus x1 multiplied by q2 minus q1, or I will put it as in a vector form minus 1 1 multiplied by q1 q2. Okay, what I had above before this was epsilon is equal to q2 minus q1 divided by x2 minus x1. Okay, I just written that in a vector form like this. Okay, and this now x2 minus x1. This is the element that I have. The x value here is x1. The x value here is x2. x2 minus x1 is nothing but the length of the element. Okay, so I'll say 1 over the length of the element. This vector is nothing but the q vector that I had just introduced. Okay, and this vector is what I get here, minus 1 1 multiplied by q. Okay, and this will say is equal to b times q. Okay, so we get epsilon to be equal to b times q, where b is equal to 1 over LE multiplied by minus 1 1, and this b is referred to as the element strain displacement matrix. Okay, if you remember earlier we had u equal to nq and epsilon is equal to b times q. So sigma is equal to E B Q. Okay, where this B is referred to as the element strain displacement matrix. And if you notice, the strain within this element does not depend on zeta, either on zeta or on x. That means this strain is constant throughout the element. Okay, so what we have got in this particular case is the strain within the element does not change. Okay, we have assumed that the deformation is varying linearly. If the deformation is varying linearly, the strain within the element will be constant. Okay, that is why these types of elements are also referred to as constant strain elements. Okay, so for simple two noded 1D elements which are also the constant strain elements, we will get J equal to NQ, epsilon equal to BQ and sigma equal to E times B times Q. And if you remember what we have been doing earlier, if we can find out U, now we can see that we can immediately get the values for epsilon and we can get the values for sigma. So in order to solve a one dimensional problem, okay, in order to solve this one dimensional problem, all that we need to do is find out the value of u in this element, or to get the value of u I need to get q. Okay, so if I am able to get the deformation at these 2 points, I can get the strain and the stresses within this element. Okay, similarly using that we will see that if I can get deformation at each of these points and so on, if I can get deformation at each of these points, I can immediately get the stress and strain variation throughout this element, throughout this body. Okay, so next time we will see that using this formulation, how do we go about getting the deformations at each of these points in the body. Okay, any question on whatever I have covered today?
Is the volume of each element same?
Volume of each element need not be. The size of the element will be taken depending on see, if I take very small elements, we will see that our computation will become complex. Okay, our matrices will become larger and so on. If I take very large elements, our accuracy will be less. So the size of the element will be taken on the basis that if in certain area, certain position, I expect higher stresses, I give it a finer, smaller element size. If I expect the stresses to be not very critical in that area, then I take a larger mesh size.
So after we've got the stresses at these points,
Yeah.
do we interpolate or do we have some solid mechanics with it?
See, we are not getting the stresses at these points.
The state.
No, we are getting a displacement at these points. Once I get the, please, once I get the displacement at these points, I can get the strains within the element by using this relationship that I have just given. Once I get the strains within the element, I can get the stresses within the element. Okay? I'll get the deformations at these points and then I'll interpolate to get the stresses and strains and so on. Okay, so I'm not getting the stresses or strain at these points. I'll get stresses within the element. Okay. Any other question? Okay, in that case that's all for today. Next time we'll do the detailed formulation of
The only variable we are solving for is the displacement.
again.
The only variable we are solving for is the displacement.
We'll solve for the displacement and then using these relations we'll get the stresses and strains. Okay.